Good morning, everyone. I would like to thank the organizer for giving me this precious opportunity. So today I'm going to mostly focus on talking about manipulation and detection of spin ordering inside antiferromagnet, particularly a non-collinear antiferromagnet. So first of all, if you work in magnetics, spintronics, you might notice that there is a strong interest these days to study antiferromagnet, trying to replace the ferromagnetic material with antiferromagnet component inside magnetic devices, spintronic devices. So there are some straightforward arguments, like in antiferromagnet, you have strong immunity to external perturbation, magnetic field perturbation, and also there are potentially some faster switching dynamics. But in order to utilize antiferromagnets, there are some very fundamental questions you have to address first. First of all, how do you represent or store information inside using antiferromagnet? So for ferromagnet, it's straightforward. You have spin up and spin down, and one is state 0 and the other is state 1. But for antiferromagnet, how do you define two distinct states? So for example, for regular antiferromagnet, if you do time reversal symmetry, meaning you flip each of the spin by 180 degrees, well, you may say microscopically you do get two different states if you can monitor each individual spins. However, macroscopically, you do not observe a net change. The reason is after you do this time reversal operation, you can simply recover its original state by translating, for example, half a unit cell, or maybe by choosing some inversion point and do an inversion symmetry operation. And then you will recover its original state. More generally speaking, so although antiferromagnet in general breaks time reversal symmetry, but it still have this P plus T symmetry, parity plus time reversal symmetry. So under such a symmetry requirement, you have this Kramer theorem, which says when your PT symmetry is conserved, for each point in the reciprocal space, it will be doubly degenerate. So for example, you can be spin up and spin down will occupy the same point in the reciprocal space. Because of that, you do not expect to see any observable magnetotransport phenomena like magnetoresistance, Hall effect, anomalous Hall effect, etc. So that was the issue. So how do you overcome this kind of degeneracy issue? Well, the bottom line is that you need to reduce the symmetry of antiferromagnetic system. So people actually have known this for a very, very long time, and then people intentionally reduce the symmetry, for example, by resorting to this kind of compensated ferrimagnetic system. So basically in ferrimagnetic system, you have two sublattices, but those two sublattices can be composed of different elements, different atoms. So for example, atom A and atom B can be, one is, for example, transition metal, like cobalt, iron, nickel. The other can be rare earth element, like gadolinium, terbium, etc. And people found that if you mix them together, you will get anti-parallelly aligned system due to their exchange interaction. And then by tuning the chemistry, you will be able to get some compensated magnetic state. So basically, in this case, you can see that the symmetry is reduced by reversing each spin, and then you will no longer be able to reproduce itself by translating or doing spatial inversion symmetry. And for example, a few years ago, we also looked into this type of compensated ferrimagnet, for example, using cobalt and terbium alloy. At a certain point, for example, the top row of the data, at 21% of terbium atomic ratio, you get almost zero net moment. But at that same composition, if you look at the second row, which is anomalous Hall resistance, you will find that there is a finite and even very large anomalous Hall resistance. So basically it works. If you reduce the symmetry, you will get some finite transport effect. You can monitor the two distinguishable spin states. But the problem is that, people study this type of compensated ferrimagnet and they realize that there is an issue. The issue is that probably we break the symmetry by too much. So you use different chemical elements, and then you completely, you break quite a lot of symmetries. So now if you compare the band structure between a classical antiferromagnet and a compensated ferromagnet, you will see that in the classical antiferromagnet, at each energy level, you have the degeneracy between up and down spins. So the density of states are equal to each other. But for compensated ferromagnet, because you lose all kind of symmetry protection, so the density of states is very different between up and down spins. So in the real space, actually, there is almost no operation that can recover the original state after time reversal. So what problem does that cause? The problem is that it's too sensitive to external perturbations. For example, you can imagine if you change the temperature of such material, then the Fermi level might undergo some small change. But when the Fermi level undergoes some subtle change, then the up and down spins are no longer exactly compensating with each other. And also, actually, you can use strain or maybe other chemical reaction to break such kind of compensation condition. So I think that's one of the issues people realize in ferromagnet. So I think that's the reason why these days people, when talk about antiferromagnet, they try to bring back some of the symmetry. So they try to make antiferromagnet, they break some symmetry, but at the same time try to conserve some other symmetry to get some protection. So as I said earlier, the PT symmetry, if you have PT symmetry inside antiferromagnet, then you will have spin degeneracy, and that's not good. So you need to break the PT symmetry. So here, since I'm going to talk about non-collinear antiferromagnets, I will directly utilize this as an example. So for example, in this type of tri-lattice non-collinear antiferromagnet, if you flip each spin by 180 degrees, you will find that you will not be able to recover the original state by either translating the lattice or do some inversion operation. So now, if you break the symmetry, then you get the lifted spin degeneracy in the reciprocal space. Then that means, to some extent, they can behave like a ferromagnet. So for example, people can get finite magnetotransport effect, anomalous Hall effect, anomalous Nernst effect, finite spin polarization, magnetoresistance, etc. But as I said, at the same time, you still want to keep some symmetry, to use those symmetry to protect the band structure so that it's not too sensitive to external perturbations. So here, what kind of symmetry do you still have? Well, basically, although you break the PT symmetry, but there are still the symmetry as listed at the bottom of this slide. You have the parity. I mean, if you just simply consider the lattice structure, it still have the inversion symmetry, and then there are quite a few mirror planes where you can do mirror operation or maybe mirror plus some time reversal symmetry operation. So here it shows that this is a one mirror plane, MX, and then this is another symmetry operation you can do, which is mirror across this Y plane plus some time reversal operation. Okay, so basically, so that's about non-collinear antiferromagnet, which is what I'm going to talk about mostly today. But here I would like to mention that these days you also heard the term of altermagnet. So usually people define altermagnetism in this category of collinear antiferromagnet, but they have very similar origin or similar physics with the non-collinear antiferromagnet that I just talked about. So the main idea is still that you break the PT symmetry. For example, here you have two spin lattices, XA and XB, but the atomic environment that those two spin lattices they say around them are different. Therefore, after you flip those spins together, you will not be able to recover it by simply translating the lattice. So that's you get this spin split in the reciprocal space, or you lift the degeneracy. But at the same time, it still has some symmetry. For example, if you do some rotation, 90 degrees rotation around certain axes, you will be able to recover the original state even after time reversal operation. So that's the reason I say it still conserves some symmetry. But the bottom line is that you get two distinguished states, then you can start to talk about anomalous Hall effect, magneto-optical effect, anomalous Nernst effect, magnetoresistance, and so on and so forth. Okay, so this is about altermagnet, but in the following, I'm only going to talk about non-collinear antiferromagnet. So here, the family of the materials I'm going to talk about is this kind of manganese 3X, where X can be a few different transition metals, gallium, tin, germanium, platinum, iridium, and so on. They have some subtle difference in terms of their real space spin texture, but today I'm going to utilize manganese 3 tin as an example. So as has already been discussed yesterday, this is in this kind of Kagome lattice structure. So for this kind of Kagome magnet, so the manganese atom occupy those corners of the triangle, and then at the same time the tin atom is occupying the center of each of the hexagon. Because of this kind of frustrated magnetism, you can imagine those three spin lattices, they cannot be in a purely antiparallel orientation. So although they have antiferromagnetic exchange interaction. So because of this frustration, so manganese spins aligns 120 degrees away from its neighbor. At the same time, this kind of 120 degrees rotation from one spin to the next spin has a fixed chirality. That's because of the Januszewski-Moria interaction. So this is the real space spin texture of this non-collinear antiferromagnet. Because of the broken PD symmetry, if you go to the reciprocal space, you will find that it's no longer spin degenerate everywhere. Of course, one subtlety here is that since you have non-collinear antiferromagnet, there is no good principal axis for spin. So you cannot, strictly speaking, you cannot talk about spin up or spin down. But instead, you have to talk about the expected or average value of along certain defined spin axis. For example, here is the color codes the spin expectation value along the x direction. Another thing I would like to mention is that this one has complicated band structure. So at the Fermi surface, there are 3 bands that intersect with the Fermi surface. This is only to show the one band. But from here, you can already see that along certain direction, along certain lobe, you will get finite spin polarization. So because of this spin split in the reciprocal space, and then people discovered finite magnetotransport effect, for example, anomalous Hall effect. Although, I mean, the symmetry breaking only tells you that there is such a possibility to get a finite effect. But at the same time, because of the Berry curvature in the reciprocal space, you get actually quite a large anomalous Hall effect. One thing that I would like to mention is that although it's antiferromagnet, but it still has very weak ferromagnetism, which is about 1,000th of a regular ferromagnet, which is very tiny, but that small magnetic moment allows you to get a handle to control the spin ordering inside this system. So actually, the large anomalous Hall effect was already predicted by Allen and his collaborators more than 10 years ago. And later on, it was discovered in various types of manganese X system. So besides this kind of transport effect, there is also the magneto-optical Kerr effect. For example, in antiferromagnet, in principle, you do not expect to see different domains. But for this type of non-collinear antiferromagnet, you are able to see this kind of 180 degrees opposite domains. And this was work done by Nakatsuji and collaborators, including Qialin, a few years ago. Okay, so today I'm going to address the following 2 questions on non-collinear antiferromagnet. One is about switching the ordering, spin ordering using electrical method, particularly spin torque effect. And the second is talk about detection of the spin ordering inside antiferromagnet using TMR effect. So first of all, what are we talking about here in terms of switching or controlling the spin ordering? So first of all, I have to say that we are not trying to completely break this kind of 120 degrees misalignment between neighboring spins, because that corresponds to very high energy level. There is no way to magnetically or electrically to break that kind of alignment between neighboring spins. What we are trying to do is just to rotate each spin by the same amount of angles, so that you still maintain that fixed misalignment between sublattices, but at the same time, the overall spin orientation get switched coherently. In order to describe such kind of switching of magnetic ordering, people develop such kind of quantity, which is known as cluster octopole. So just like if you have a single spin, then it's described by a dipole. If you have two spin lattices, then it's described by a quadrupole. And if you have three spins, then you need to describe it by an octopole. In principle, this octopole is a high-order tensor, which is super complicated. But people found that if you can constrain your discussion to within the Kagome plane to talk about those kind of coherent rotation of all of those three spins, then you can come up with this kind of effective vector. They call it this octopole vector. And this octopole vector actually captures the coherent rotation of all of those spin lattices. At the same time, experimentally, you will find that this so-defined octopole moment will be mostly parallel with the net magnetic moment. So it does have some physical correspondence. So what we are trying to address is try to utilize electrical method, particularly spin torque, to induce such kind of rotation of the octopole moment, or in other words, the three sublattices coherent rotation. So here, I would like to give one slide background introduction about the electrical manipulation of magnetic moment through the spin torque effect. So if you do not work on spin torque, then generally speaking, spin torque is the effect of resulted from angular momentum conservation. So basically, if you have a sandwich structure made from two magnetic layers, you can use one as a polarizer layer, which generates these polarized spins. And when those polarized spins enter the second layer, they have to be aligned along the local magnetic moment direction. So in this process, they will exchange their angular momentum. So you can imagine if you apply larger enough current, the second magnetic moment layer, the layer of the second magnet will get switched. So this is kind of reflection or conservation angular momentum. And then, of course, mathematically it can be described by more rigorous language, like using this kind of damping like torque, which is like a negative damping. So this is, in general, how you can control a ferromagnet moment using electrical current through the spin torque effect. But of course, aside from polarizing the current using one magnetic layer, you can also generate spin current using this spin orbit interaction of specifically spin Hall effect. Spin Hall effect is when you apply a charge current longitudinally. In the transverse direction, you will get some spin polarization. And now if you put a ferromagnet dipole adjacent to this spin Hall material, then the generated non-equilibrium spins can also exert a spin torque effect onto the adjacent moment and then lead to this kind of magnetic switching. So the spin torque switching using spin Hall effect on ferromagnetic system has been studied over the past more than 1 decade. Okay, so now the question is how can we utilize such kind of spin torque effect on the antiferromagnet? Well, basically in order to rotate those three spin lattices coherently, we have to grow the film in a appropriate configuration. So if you do some analysis, you will find that there is only one configuration where the spin torque can exert a constructive influence on the three lattices. That's the configuration where the Kagome plane or the easy plane of spins stand perpendicular to the film surface. So only on that configuration, your injected spins will be perpendicular to this easy plane and then rotate the three sublattices constructively. So it's not a very trivial task to grow this kind of Kagome plane perpendicular to film surface film. So you have to do some epitextual growth because naturally those kind of Kagome lattice will prefer to grow along the C-plane. So with the Kagome plane parallel with the film surface. So here we utilize MgO and as single crystal substrate and tungsten as some buffer layer. So through XRD, we can verify that there is an epitextual relationship enforce the Kagome plane to be perpendicular to the film surface. So after grow the film, we can also verify with anomalous Hall measurement to say that it is the desired antiferromagnetic state with a large Berry curvature and all the other properties consistent with previous studies. Okay, so after we have this kind of manganese 3-tin film in this special growth crystal orientation, we can grow a thin layer of platinum on top, which provide the spin current or the spin orbit torque. And then we can utilize, by applying a current inside the platinum, we can try to switch this magnetic octopole in this system. So this schematic gives you a rough idea how does the spins interact with each other in such configuration. So the current I, the black arrow, is a charge current applied direction inside the platinum. And then this green arrow of sigma represents the injected spin from the spin Hall effect into manganese 3-tin. And then this sigma, it will interact with each of the 3 sublattices. So you can characterize their interactions through such kind of effective field from damping-like torque. Sorry, it's a little bit complicated terminology here. But the bottom line is that you can understand the effect as an effective field. And that effective field comes from the cross product between the moment of each sublattice with its spin. So basically, you can use your right hand to verify that the effective field on each of the sublattices try to rotate the spin sublattices, the spins in the constructive manner. So both, for example, or in the counterclockwise direction. And then you can imagine that you can realize this kind of overall switching. So this is experimental data. So when you apply a charge current, we do see such kind of switching, reversible switching of the Hall resistance, which represents the spin ordering. But this data looks almost exactly the same as regular spin orbit torque or spin Hall effect switching of ferromagnet. So people might say, hey, because you have weak ferromagnetism, and then this is just a simple switching on that weak ferromagnetism. So what's the difference? How do you know that it's through those kind of individual sublattices that you control the ordering inside the antiferromagnet? Well, actually, we do see one major difference between the switching of this non-collinear antiferromagnet and regular ferromagnet. That is, in the regular ferromagnet, if you determine the switching polarity, you will find that the current-induced switching and the field-induced switching have the same polarity if you define the current and field orientation in a certain way. And under the same definition, you will find that for this non-collinear antiferromagnet, the spin torque-induced switching actually have the opposite switching polarity compared with the field-induced switching. So basically, that is summarized in this schematic. If you try to switch a ferromagnet dipole, and then the same current will switch the moment from down to up. But now if you try to switch the octopole moment, the same current will switch the moment or the octopole moment from up to down, or the net moment from up to down. So basically, they are just opposite with each other. So how do you understand that? Well, basically, this left side schematic might provide some insights. So for ferromagnet, the induced effective field try to rotate the moment in a clockwise direction. But for the non-collinear antiferromagnet, although the spin torque try to rotate each spin in the same clockwise direction, however, the overall octopole moment or the net moment of this system rotates in a counterclockwise direction. So basically, that is kind of the handedness difference between switching a ferromagnet and switching an antiferromagnet. So colleagues in the field, they come up with this kind of interesting analogy where they talk about the 3 sublattices using 3 small gears, and they talk about this overall ordering parameter of the octopole moment using the central big gear. And then you can see that when each of the 3 small gears rotate in clockwise direction, and the central gear rotates in the counterclockwise direction. So I think this is an interesting analogy. So there might be some deeper level correlation among them. But anyway, so far I'm talking about how to manipulate spin ordering inside a non-collinear antiferromagnet manganese 3-tin. In the following, I'm going to talk about how to detect the spin ordering inside antiferromagnet through a tunnel magnetoresistance effect. So earlier, as I said, because of the broken PT symmetry, so now in the reciprocal space, you can have spin splitting, you can have finite spin polarization along different directions. The bottom line is that if you integrate over the whole Fermi surface, you are still going to get zero net moment, because the reciprocal space net moment and real space net moment have to be equal to each other. So if you have zero average spin or zero average net moment, how are you going to get, for example, tunnel magnetoresistance? Well, one important feature for tunnel magnetoresistance is that electrons located at different regions of the reciprocal space, they will contribute differently for the tunneling current. Particularly for electrons that is located in the center of the projected 2D brane zone, they will make the largest contribution because they are mostly moving forward. But for electrons that is located at the side of the or edge of the projected 2D brane zone, they are not going to make much contribution because their effective trajectory is kind of over a very long distance inside the insulator. So that is a very small contribution. So this right side schematic roughly shows this idea. So for example, when you have the ferromagnet movement along one direction, because of spin matching requirement, then the electron in the center of the brane zone will tunnel through. However, if you flip the ferromagnetic orientation, then spins on the edge, on the side of the projected brane zone need to tunnel through, and then that's much smaller tunneling probability. So basically, this is the idea of how you can get a finite tunnel magnetoresistance between one antiferromagnet and one ferromagnet. So basically, we build such kind of magnetic tunnel junction structure using manganese 3 tin as bottom electrode and cobalt boron as a top electrode, MgO as a tunneling barrier. So although this structure sounds simple enough, but in terms of real fabrication, it's kind of a little bit involved. The reason is in order to get a crystallized tunnel junction, you have to do some annealing. But manganese is known to be very volatile, so they tend to diffuse around when you heat up the sample. So in order to suppress such kind of manganese diffusion problem, we did this kind of deposit, etch back, and then deposit again process to grow this whole MTJ stack. Okay, so after you get this stack and do some nanofabrication, define a magnetic tunnel junction, so we can start to measure the tunnel magnetoresistance. So as shown in this middle figure, there is a finite and actually even quite large tunnel magnetoresistance. So when we sweep the in-plane field, we actually flip the orientation of this cobalt boron free layer. And you can see that we get about 300% TMR. This is a low temperature, but this is already kind of comparable to regular TMR you get from ferromagnetic only MTJs, magnetic tunnel junctions. Another interesting feature that we observe is that the angle dependence is quite strange, because usually when you rotate the magnetic field in the plane, you get 360 degrees periodicity. So the highest and lowest resistance happens 180 degrees apart. But in this case, actually, it's about 90 degrees apart. And then if you count the highest and lowest point, actually the MR magnetoresistance is even larger, almost 900%. So why is this? There is such kind of strange angular dependence. We don't fully understand yet. So finally, antiferromagnet, as I said, the advantage you expect from it is that it should be more immune to external perturbation. So here, for example, when you do this kind of high field minor loop measurement, you will see that there is only the switching corresponding to the cobalt boron, but the antiferromagnet is much more robust. So far, we are only able to get high TMR at low temperature, for example, 10 Kelvin, 20 Kelvin. But as you increase the temperature close to 200 Kelvin, this TMR suddenly disappear. So, I mean, obviously there is still some optimization work need to be done in order to bring this effect up to room temperature. So finally, this is a summary. So basically, if you want to get some usable antiferromagnet, you need to break the PT symmetry. But at the same time, there are some other symmetries that can protect the electronic structure. So we can utilize spin torque to control the spin ordering. At the same time, we can utilize tunneling magnetoresistance to probe the ordering of such non-collinear antiferromagnet. That's all. Thank you for your attention.
We have time for maybe one or two very quick questions from the audience.
So I have two quick questions. First one is, why can't you detect the magnet by just measuring the Hall resistivity? Why is that not a good way? And second question is, can you comment on, how far this strategy for making a technology is, how advanced it is compared to the collinear altermagnet strategy?
Yeah, so I would, well, for the first question, why don't we just utilize anomalous Hall resistance? Why do we want to develop some magnetic junction? So the reason is, I think, so far, the anomalous Hall resistance is still quite small, let's say in a few ohm case. Also, you probably need to make a 4-terminal device in order to do it. So in practice, circuit designer don't like that. Okay. So MTJ is probably so far the only practical way to make memory or logic devices. So the second question is the non-collinear antiferromagnet versus altermagnet, collinear altermagnet. Personally, I think they have very similar physics. So there are quite a lot of learnings that can be shared among them. In terms of technology advancement, I think non-collinear antiferromagnet is a little bit ahead, in the sense people have observed anomalous Hall resistance, magneto-optical effect, even TMR here. But for altermagnet, I think there are still some struggling in get some conclusive evidence about, for example, in some materials, whether the anomalous Hall resistance is from the altermagnetism or not. There are still some disputes. So that's my understanding. Yeah.
Yeah. Okay, for the interest of time, let's thank our speaker again. Our next speaker is Lucas Carreta. He will be telling us about the non-trivial polar phenomenon.